So, good evening, students. Welcome to week 11 problem solving session for Analog Electronics Circuits course. I'm Diyasharda Devi, a PMRF fellow. So, in today's session, we'll be talking about something very important, that is stability, right? So, when we talk about stability, stability is very important for any system. And the first question that arises is, what is stability, right? What is stability? So, in technical terms, when we talk about stability, so stability basically means that when you have a bounded input and it gives you a bounded output, then we call the system to be stable. Okay, so that is the idea of stability. Now, basically, the thing is your output should be controlled. So, your output needs to be controlled. That's when your system is stable. Now, let's say, for example, if this is your input, corresponding to this, if you get an output, let's say somewhat like this, but it retains. So, if this is your output, then your system is stable. But let's say for this input, you get an output like this, right? Then this makes your system unstable. Okay. With this concept, so basically, when we talk about these input output relations, so for a step input like this, we have different scenarios that can be possible in terms of how your output will look like. Okay. So, for example, uh, there are four possible cases corresponding to the particular step input, and there will be four different types of output which are possible. So we'll look into them. Okay. So the first condition is, let's say your output follows the input and it comes close to, like it is almost equal to your input. Okay. So red is denoting output and blue is your input. Now, there can be another condition where it is like, first of all, your output rises slowly, then your output rises slowly, it increases, goes beyond your input, comes down, and it basically oscillates across your input, and at some infinite point, it will stabilize and come closer to your output value. This is the second case, right? Now, third condition is, again your output slowly increases, then it comes down, again it increases, it comes down, but rather than stabilizing or rather than reducing amplitude, what happens is it oscillates continuously across your input, but it is not settling down. Okay, so this is the third condition. And the fourth and the last condition is your output slowly increases. It goes up, comes down your input value, but this amplitude starts increasing. So basically, your output is increasing. Okay. So this is the fourth condition. Now, to name them out, so first of all, the first condition, we call this an overdamped system. Okay. The second one is a damped system. Why damped? Because its output is slowly reducing, right? So when there is a reduction, we call it as damping effect. So that's why it is damped system. Now, this particular system, so if we talk about stability, so see the first condition, your output reaches the input. Hence, it is a stable system as your output is bounded with bounded input. Second condition also at infinite time scale, if we talk about steady state, again, the output is stabilizing. So that's why this system is also stable. Now, when we talk about this third condition, here the thing is, unfortunately, your output is not like it is not approaching your input. So basically, it is not bounded in the sense that your output is not coming close to input, but also if you observe that it's simply oscillating across that input point, right? So this system is somewhere in between uh, a stable system or an unstable system. Hence, we call these kind of systems as marginally stable systems. Okay. So this is a marginally stable system. Now, when in the last case, you see that your output is continuously increasing. So it is going out of bound, right? So it's increasing. So if you imagine about an infinite time, your output will reach to infinity. So which basically makes your system unstable. So this particular system is unstable system. Okay, so these are the primary four outputs that you can observe for a given input. Now, where do they come from, right? So this is basically, we know that input output relation that we get, it is from the transfer functions. And we also know that transfer functions are predominantly defined by basically their roots. And one of the most important thing about a transfer function, or most important root of a transfer function, a solution of transfer function, is pole, because your stability depends on poles. We'll see how, but for now we know that okay, this is something that is happening because of the poles orientation, like where the poles are placed. Depending on that, you will see certain behavior, any one of these four behaviors, right? So if we talk about this first system, so here when there is an overdamped system which is completely stable, the behavior of poles is like the poles are real poles, okay? In case of overdamped system, you obtain real poles. In case of damped system, these poles will be an like so these poles will be in the form of sigma plus minus j omega. Okay, so this is the behavior of poles when you have an overdamped system. In case of marginally stable systems, what happens is you only have your poles which have imaginary part. So the overdamped system has only real part in their roots. In case of damped system, you will see both real as well as imaginary part in the system in your roots or in the pole value. When you have a marginally stable system, you will only have imaginary part of the root. And then when you have unstable system like this, you would observe that these poles are in right hand side of the plane. Now, which plane am I talking about, right? So, what is the plane that we talk about in terms of poles and zero placement? So, it is not a simple XY plane. Rather, we call it as S plane. Okay. So, in that S plane, so we have S plane. So, how do we draw S plane is we again have two perpendicular axes similar to any plane. So, here when we talk about this plane, so it has the real parts of the roots are represented on the x-axis, whereas the imaginary parts of the roots will be represented in the y-axis. Okay. Now, when I say my poles are, so poles can be real, imaginary, or they can be of the form of conjugate pairs. And when I'm talking about the systems, so these systems are basically second order systems, okay? I'm talking about a second order systems. We'll also discuss why stability is a concern for second order systems. Stability is never a concern for first order system. First order system, by that I mean only one pole. A system with single pole is first order system. If a system has two poles, then it is second order system. So in case of first order system, it is always stable. So maybe I can um, write this down. So first order system is always stable. Okay. The stability is a concern for higher order systems starting from second order. We'll discuss why, and I'll take that up based on phase margin idea, which will come very soon. But for now, it is like the first order system is always stable. All these output behaviors that we have observed till now, these are for second order systems. Like your system will have two poles. Now, in S-plane, if you observe this S-plane, where are the possibilities that you can place two poles, right? So your system can, your poles can either be real poles. When it is a real pole, that means it will only come across your x-axis or the sigma axis. Those poles are called real poles. If your poles come on the y-axis, only y-axis, that is the j omega axis, then your poles are imaginary poles. And the third is you have a conjugate pair, so which will be of the form sigma plus j omega, right? So j omega, yeah. So when these kind of poles are there, that means they will come somewhere in between. Like for example, let's say I have poles here. We know that these are um, so we would have two poles, and these poles can be anywhere. So let's say I say my two poles, which are real poles, are present at my sigma axis. So that means these are real poles. And so if you see that anything that is on the left side of this plane, okay, so anything on this side of the plane is stable. Still, it is stable, okay? Somewhere or the other, this is stable side. Whereas when you have poles on this side of the plane, they are unstable. So any pole, if you have a system, you found the transfer function, then you find the pole of that system. And if your pole comes out to be with a positive sigma, right? That is the positive real part. So anything with positive real part will come on the right hand side, right? So this is unstable region. And this particular region is stable region. Okay? This is something that we always have to keep in mind. Now, instability, as we discussed, we have overdamped system, damped system, and marginally stable system, which is like this. So if you see the pole placement, we find that, okay, this part has only real parts, right? So only real roots. That means this is overdamped system, right? Now let's say I have two poles, one over here and another over here, because whenever you have these poles like in form of sigma j omega, they are most of the times they are conjugate pairs. So if you have a positive part, so it will have its image mirror image on the negative side as well to balance that conjugate pair. Now, when you have two poles, P1 and P2 like this, so here you can see that these particular poles will have both sigma as well as real as well as imaginary parts. So this will again, these are again stable systems, but here this is for a damped system. So your system is damped over here. Now the third condition is when you have poles on the j omega axis or the perpendicular y axis, then here the poles are for a marginally stable system. That means if you obtain poles with only imaginary part with zero real part, you can understand that your output will be continuously oscillating. Other than that, if any of the poles appear here or it has real pole with like real part is positive, then all these poles are unstable. So the moment a system is unstable, then other analyses are never important because we can simply discard the system. And this is how you can understand, okay, what is happening with the system. So now, so this is the real axis. This is your imaginary axis. So this particular graph that we have drawn is very important while analyzing your stability, system stability. And this is mostly this is covered in signals and systems that system stability kind of systems based courses. But yeah, for analysis of stability, this is the key, what should I say? This is the key concept for analyzing the stability. Okay. So now when we talk about this two-pole system, so how will your transfer function look like, T of S or H of S? It is somewhat like A S minus P1, S minus P2. So this will give you LHS. Okay, so this will give you RHS poles. Why RHS poles? Because you will get positive P1, right? Here S equal to P1 and S equal to P2. Since these are positive poles, so it will come in the right hand side. Now, similarly, when your transfer function is of the form S plus P1, S plus P2, then this will give you a left hand side pole with S being minus P1 and S being minus P2. Okay. And these are second order systems. So order we define by the number of poles. If the system has three poles, then it is a third order system. If it has four poles, it is a fourth order system. So based on number of poles, we call it with the number of order of the system. Now, so this is the basic idea of stability. Whatever the system you have, you analyze your stability based on this. Now, we know that in our systems, most of the times we use feedback, and it is either positive feedback or negative feedback, right? So, we have feedbacks in our system. Let's say, let's first analyze Based on these concepts, whether your system will be stable or unstable. Okay. So, so this is a simple system where you give your input, you get an output, and this particular system has a gain of A. Okay, this is the basic system that we all know. Now, let's say I provided a feedback. So, what is the meaning of feedback? Is basically you take some portion of your output and you feed it to the input as an error function. So, right. So, let's say it has a factor of beta. So, this is your feedback part. So output to input, we call it as feedback path, and input to output is feed forward path. Okay, so these are the nomenclatures. Technically, people use it. So if you can keep it in mind, right? So now, yeah. So this feedback, you can add your output to input with 0 degree phase shift, that is positive feedback, or you can use a 180-degree phase shift, which is basically negative feedback. Okay. And we'll analyze both of them and we'll see the effect, right? So maybe let's start with the positive feedback. Okay. So when you have your positive feedback, here you will have a V in, here you have V out, correct? So from feed forward path, we know that V out equal to A into V in, correct? Now, this A into V in, that is V out, that comes here. It again gets multiplied with beta and we get beta V out. So at this point, at the input side, now what you have is V in dash, that is in the next stage, next round. It will have V in plus beta V out, that is V in plus A into beta V in, correct? This is the input after first iteration. Now, yeah, so this is after first iteration. Now, let's say second iteration, okay? So in second iteration, my V in dash is the new input. So it will go to my V out. So my V out dash will become A times V in dash, that is A 1 plus A beta V in. Now this is again being fed to your input through the feedback path. So now V in double dash will be V in plus beta times of V out dash, which makes it V in plus A beta 1 plus A beta V in, right? Now let's do one more iteration and then we'll stop. So, yeah. So now if we talk about the third iteration, in this third iteration, what will happen is your new Vin is Vin double dash, and your new output, that is V out double dash, will be A into Vn double dash, right? Now, this is A into 1 plus A beta into 1 plus A beta Vn. And again, when this passes through the feedback path, you will get the new input as Vn A beta 1 plus A beta 1 plus A beta into Vn. Now, if you observe carefully, the input that I provided was only Vn, correct? But if you see the output, again, so your V out triple dash is A times of Vn triple dash. Now you see, with that input, what I provided, your output is increasing significantly. Because ideally, my output, what I wanted was, because of the simple system, it would have been A into V in, would have been my V out. But now, with this positive feedback, your output is continuously increasing. So imagine that this is the scenario for the third iteration. What will happen when you have a scenario of, let's say, 10 iterations, 100 iterations, 1000 iterations, similarly, infinite iterations? Your output is increasing continuously and it goes out of bound. So this becomes the scenario similar to this condition of 4, right? So which makes this an unstable system. So this makes it a unstable system. So this is an unstable system. That's why we
Uh,
say that, yeah, positive feedback gives us an unstable system. Okay, yeah, question?
yes, please. So, this would depend on the value of A beta as well, right?
But
I mean, if it is quite less than one, then can we also say then also system is unstable?
uh, if it is less than 1, then okay. So mm, I understand where you are coming from, because if it is less than 1, these factors will become smaller and smaller, so it will not go out of bound. That is true. But generally, we don't have systems with gain of less than 1. It's very rare, because we'll talk about it most of the times. So, where you use feedbacks, right? You use feedbacks for amplifier circuits or oscillator circuits, or when you have basically the error correction and all that,
Right.
controller circuits, control systems. So, basically, there you need the feedback. But that is definitely true that your this thing will not go out of bound when you have um, like A as well as beta less than 1. But most of the time, we generally never use attenuators much. We most of the times want amplification, right? Because we don't want to lose anything. That is also one thing, one way of looking at it. But other than that, yeah, definitely, because the moment these factors will go down, so it will become almost like a stable system. But that rarely happens. So that's why we say that our positive feedback is always unstable. But that's a good point. Like, It definitely depends on A into beta, like A and beta values. So yeah.
Right. Thank you.
Okay. So in this system, we found out that okay, this particular feedback, which is the positive feedback, it makes your system unstable. Now, the second type of feedback we have is a negative feedback. So, negative feedback basically means that you're feeding your input with a phase shift of, let's say, 180 degrees. Then it will become a negative feedback system. Now, here you have negative feedback. So, with this negative feedback, let's again analyze this input output relation. And for the first stage, so starting with, we have V out as A beta, sorry, A into V in. As again, you will have V in over here, V out here. So now this V out is being fed here. You get beta V out here. But see the new V in, that is V in dash, is V in minus of beta V out. That is V in minus V beta V in. 1 minus K beta into V in. So this is the idea. Now, again, when this is fed, so first iteration, your V out dash is A into V in dash. So this becomes A 1 minus A beta V in, and V in double dash will become A into beta 1 minus A beta V in. For second iteration, we are double dash becomes A in double dash. So this becomes A square beta 1 minus A beta V and V triple dash becomes V minus beta V. We are double dash. So that is V minus A square beta square 1 minus A beta V. So here what happens is, if you observe very carefully, your output is always reducing because of this negative values. And definitely this is true for all values of A into beta. Now here you don't have a foundation that it needs to be an attenuating system. So this, first of all, your output is not going out of bounds. So this makes the system a stable system, that we all agree, right? So this becomes a stable system. So this is a stable system with negative feedback, correct? And this is true for all values of A into beta, right? So it can be less than 1, greater than 1, any value. And here, since the system is always bounded, the output is always bounded. So the question arises, where do we need negative feedback, right? Why do we need to reduce the output? So earlier we were getting V out as A into V in, right? If say I want an amplification operation, so amplifying it by a factor of A is good for me, correct? अगर मुझे amplify ही करना है, if I want to amplify something, I want it to be amplified by the factor I have designed the amplifier already, right? Why do I need a feedback to start with? So the question, this comes from the concept of, so this is basically true with your op amps. Okay. So in op amps, what happens is, so yeah, here, why do we need this? Is first of all, if you have something to track, like if you want to track the errors or things for your controllers, you will use these things, right? You will use this feedback to track the errors and everything in a system. When we talk about our circuits, particularly analog circuits that we have, most of the circuits we deal with are amplifiers or oscillators. So there, why do we need feedback? Especially, why do you want to reduce your output, right? If I have designed an amplifier, then why do I want to reduce its amplifying factor? Because at the end, if you observe a negative feedback, you get a reduced output, right? Your amplification basically reduces. So if I talk about, so let's say, um, you have this system where your open loop gain, we call it OLG, that is open loop gain, it is A. Like when there was no feedback, the output would have a gain of A. Now, with positive feedback, the closed loop gain, that means with feedback, okay, becomes A1 minus A beta. With negative feedback, the closed loop gain of the system becomes A upon 1 plus A beta. So you see, basically what is happening is the cumulative gain of your system is increasing with the positive feedback, but the gain is reducing with the negative feedback, right? So the question arises, why do you want to reduce your gain, right? You already have a system. Why do you want to reduce the gain of your system? Let's say I have an amplifier. That amplifier has a gain of 1000 dBs. So it's very good for me, right? It will amplify small signals to very large range. Correct. But why do I want to reduce my uh, gain of the system? So basically, you use negative feedbacks for amplifiers. So this is used in amplifiers. So all your advanced amplifiers have negative feedback, or to start with, even the amplifier has a negative feedback. And the positive feedback we use for oscillators. So the question is, why do I need amplifier? So it is like, if I talk about an op amp, So what happens is in an op-amp when there is no feedback, okay, it is a open loop system, then your output versus input characteristics that we have, we call it the characteristics, right? So this output characteristics is like, so this input output behavior of uh, open loop open loop op-amp, that is without feedback, looks like this. Okay, this is how your op-amp's open loop transfer function will look like when there is no feedback, right? Now you see for a very small input value also your output is saturating. So you will always get a fixed output, right? And this range is very, very small because open loop gain of an op-amp is quite high. So it's like 10,000, 100,000 volt by volt. So it is like 1000 dBs or 500 dBs or even more. So to get that range, and if you want a sine wave to give you an amplified sine wave as output, imagine how small that input should be. Like it should be in somewhere like 10, femto volts or even smaller. Correct. But when you have an op amp with feedback, so op amp, say with negative feedback, op amp with negative feedback. So what basically happens is you widen this range, okay? Because you have reduced the gain, so that basically means that now the input that can be satisfactorily amplified by your op-amp system has increased this much. Earlier it was this small. So getting my point. So this is the need for your feedback. Now imagine if it was a positive feedback. So what would happen? This input range would further reduce. You can observe it, right? Because the gain is increasing even more. So it will saturate the output even before. So the input span will reduce even further. So that's how you utilize this feedback for in case of your op amps or in the amplifier system. And we have already seen that this gives us a stable system. Whereas this is not the case for and like this is not the case for oscillator. In the oscillators, what happens is you don't give any input, okay? But your oscillator gives you an output. So what happens is because there is a positive feedback, you know that your output is increasing continuously because of this positive feedback. So it picks up some noise, some thermal noise, which is very, very small. Then what happens in an oscillator is it starts increasing that noise. until it reaches a certain level that it is like, so that's basically the steady state. And in the steady state, you will get some output out of your oscillator. And that is possible only because of the positive feedback. Okay. So that is the basic idea of this. Yeah, that is the basic idea behind these feedbacks. Okay. So now, see, if I talk about like the values per se, so we can solve this based on values also. So if we solve based on values, we can get even clear picture about what is the range of inputs. So depending on that, what is the value we want for our like transfer function as well as the beta. So let's say if my beta is 1 in both the cases. So if beta becomes 1, my closed loop gain for positive feedback will becomes 1 upon, sorry, a upon 1 minus a. So this is definitely greater than a, and the same closed loop gain for my negative feedback will become a upon 1 plus a, which is always less than a. And if we know the value of closed loop gain, then we know that, okay, so in case of op-amp itself, we know that output will saturate at VDD and minus VDD. So plus VDD and minus VSS. So when we know this, we know, okay, the limits for our output. So if we know the limits on our output, and we also know the gains from these closed loop gains, so we can find the range of inputs that can be provided. So this is similar to the swing analysis that we did. We said that our output should not be clipped or should not be like it should not, there should not be any distortion in the output. So based on that, we found the swing. And if you know the swing, you know the gain of your circuit, you know the gain of your amplifier, then from there, when you know all these values, you can come to like come to find the input range, right? And we have also seen like in differential pair, we have talked about um ICMR, the input common mode range we did, right? So it basically talks about the input ranges that are uh, feasible for your system. So it comes from your output swing, your gain analysis. So that's how you utilize this particular information to find the range of inputs that can be provided to your circuit, because it is very important, as the signal strengths are different. So it's not like you have, like, let's say you use some sensor to sense the systems, right? Like you use, let's say, temperature sensor. So temperature sensors will have very small signals, few microvolts or few microamperes. Those signals are given to your amplifier to satisfactorily amplify that particular input. Your op amp or whatever your amplifier is, it should be designed in such a way, right, that your output is satisfactorily mimicking the input. It's just amplifying the value rather than introducing any sort of distortion. So all those information comes from these things. Okay. So yeah, this is the idea with the based on stability, feedback, and everything. Now, theoretically speaking, how we define whether our system, whatever circuit we have, is stable or not. Okay. So for that, we perform a phase margin analysis. We analyze the phase margin. We all know the phase, right? So when you have a transfer function, you can find the phase of that transfer function. How do we find the phase? So let's say my transfer function is a plus j omega, for suppose, like, or it is simply s. Okay? Then my phase of that particular system is tan inverse omega by a, correct? Tan inverse omega by a. So this is how you find the phase of your transfer function. So when I say phase margin, so margin, we know margin basically means that how much we are left with the deadline or the end, correct? So we find this phase margin with respect to 180 degrees. Okay, so we see the phase of transfer function when the gain of transfer function is 1 volt by volt or 0 dBs. So we talk about or we look into the phase when your Bode plot basically crosses 0 dB line, or when the gain of your transfer function is 0 dBs. So the frequency at which your gain is 0 dB, at that frequency you find the phase of the system, and then you find phase margin. So phase margin is basically 180 degrees minus the phase of transfer function at 0 dB frequency. This is how we find the phase margin. Okay, so if here now, how do we define the stability? So if phase margin, that is PM, is less than or equal to zero. If phase margin is less than or equal to zero, we say the system is unstable. Okay. If phase margin is greater than zero, then the system is stable. Right? Higher the phase margin, more the stability. So higher the phase margin, more stable the system. So the more the phase margin that you have, more the stability will be. That's how you define the stability of your system. Okay. Now, why did I say that a single pole system would always be stable, right? So let's analyze it. So first of all, let's take a first order system. So the transfer function is a by. I'm only taking a positive pole system. No, sorry, uh, left-hand side pole system. So I'm talking about a stable system, and then we'll have this, which is also a single pole system. So S plus sigma, let's say. Okay. So yeah. So how will your phase of the system look like? So this A introduces a phase of 0 degrees minus tan inverse because it is in denominator. So that's why minus tan inverse omega by sigma, right? This is how you will find the phase of the system. Now, what is the maximum phase that you can obtain? So let's say if my sigma is 0, that makes my tan inverse omega by 0, which is tan inverse infinity. So this is 90 degrees, correct? So the maximum phase that can be introduced either by a pole or a zero is 90 degrees. Since it is a pole, the phase introduced by the pole would be minus 90. So maximum phase that can be introduced by a pole. Now, if I talk about a zero system, let's say this is my system, right? So it only has an imaginary part, but it is in numerator. So which introduces a phase that is maximum of plus 90 degrees. Correct? So if you have a single pole system, the maximum phase that can be introduced is minus 90 degrees. So if you have to calculate the phase margin, it is always 180 minus 90 degree max. So that means your phase margin would be greater than or equal to 90 degrees, correct? So this is definitely the maximum phase margin that you can obtain. And also this is something which is definitely a positive value, right? So this gives a stable system. So that's why we say that first order systems are always stable. And whatever, uh, yeah, so whatever is the frequency range, wherever you take the uh, phase margin, it is always stable. So phase margin is stable for a first order system. That's why we are never concerned about our first order system. What we are concerned about is a second order system, right? So the thing is, see, you have two poles now. If max phase by one pole is 90 degrees, then by two poles it would be 180 degrees, correct? So if we reach this maximum, then phase margin becomes 180 minus 180 degrees, that is 0. So which brings us to an unstable system, correct? So that's why there is a possibility that your two pole system might be stable or might not be stable, depending on how the phases appear in the system, right? So this is how basically we identify whether the system is stable or not. Okay. Now we know that your Bode plot has both uh, like a phase plot as well as a frequency plot. So the idea is, let's say this is your magnitude plot and this is somewhat like this. Okay. And at this point, it is crossing a 0 dB, 0 dB frequency, right? So if I can make sure that at this particular frequency, whatever my phase is, this phase is less than this phase, this phase at this point should be less than 180 degrees. Okay. If at this point my phase is less than 180 degree, I have to design my system, then my system would be stable. So that's why now see if your poles lie before this 0 dBs. Like if your both the poles lie here, then definitely at this point your phase would be more than 180 degrees. Correct? But now, when your one pole lies here, another pole lies after your 0 degree point. That makes your system as a single pole system, right? Predominantly, there is one pole at least before 0 dBs, correct? So this makes your system a stable system. That's why it is very important to understand and to know the placement of the poles, like where these poles are placed. Depending on that, it will define the stability of the system. Okay. So, and we also like if there is, let's say you have a two-pole system, but your system is becoming unstable from the phase margin perspective. So, what we try to do is we try to separate the poles by using some method or other, by introducing a pole zero compensation or something. There are different methods that can be used. Like you can introduce a zero in between. So if you introduce a zero in between, then things change. And likewise, so you introduce, there are few methods through which you compensate these poles and zero placement and try to make the system stable. So that is a different topic. But yeah, there are things that can be, or there are certain um, modifications that can be performed in order to stabilize the system. Okay, so now when we have a two pole, yes, if you have any doubts, please unmute yourself and ask.
Uh, so yes, I just wanted to know. So at least one pole should be before the crossover frequency, right? Like,
Yes, yes, yes. At
uh,
least one should be before the crossover frequency, and that pole is also the dominant pole.
so by dominant, do we mean like it should be quite like far away or
No, no, it's
have?
the closest pole. The first pole is the dominant pole. So the closest
Yeah,
pole, because after that you start seeing a drop in your gain, right? So your
yes.
bandwidth and everything is more or less related to the dominant pole. So that's it.
So I mean, like, how far should it be from the frequency, the crossover frequency? Some rough estimate.
I mean, we cannot comment on that much, but definitely see from a practical perspective what I want. Um, I want, first of all, my bandwidth to be high. Let's say if I'm talking about my amplifier, I want my bandwidth to be high, right? So
Yes.
if I say my transfer function for my system is somewhat like this, so I want like my maximum region I could get to be of a flat gain so that it does not introduce any distortions. So this is my bandwidth, right? And
Yes.
this is because of the pole that we introduced. So I want the highest possible bandwidth that can be obtained. Correct. So that for that I want my pole to be as far as possible from my um, like as high as possible to get the higher bandwidth. And it does not matter much like how close your frequency is to the crossover frequency, like how close your pole is to the crossover frequency. It's more important that how far apart your two poles are, because that basically uh, introduces the stability. If the poles are close to each other, then the chances are that your phase margin will reduce. As far away
Uh,
the poles are, then you would get a phase margin of, because it becomes a single pole kind of system. Because your crossover will be earlier and then your second pole will appear. So it becomes a single pole system. So the separation is very important, the separation between two poles
yes,
for the
so that is
stability.
what, like, if it is very near to the crossover frequency, then we might get into the zone of like instability, right? So we want it to be quite far apart, and for
Yeah,
having that,
definitely they should be far apart. And also, your second pole should come after the crossover frequency. It should come
okay,
after crossover frequency.
right. But in that case, let's say, I mean, we are reducing the bandwidth. So is like there is a trade-off between if the pole is quite the dominant pole is very far apart from the crossover frequency. So is there a trade-off between like this bandwidth and stability thing?
Bandwidth and stability, I mean, no, there is no direct relation as such. But I mean, see, if you don't have any pole before a crossover frequency, then how would the crossover happen? That is not
Uh,
possible, right? Why the
yeah. So
crossover happens is because of the drop that appears due to the presence of a pole. If there is no pole in your system, then it will be a straight line, right? So
yes. So
definitely there would be one pole, at least one pole present before your crossover frequency.
yes.
But
What I mean is,
what, huh?
sorry. What I meant is like if it is reducing like very fast, let's say with a very high slope, then in that
Huh.
case, I mean, we can have a, let's say and it happens at a very high frequency. We can have the first dominant pole very near to the crossover frequency, right?
Hmm.
Uh, but the chances of instability will also increase in that case. Is it so?
I mean, see, the slope with which your graph will decrease, it also depends on the pole. If you have multiple poles, then only the slope is very steep. So if you have a
Yes.
single position where you have two poles, the drop will be minus 40 dB per decade. If you have three consecutive poles at the same point, then it will be minus 60 dB per decade. If it is four, then it is minus 80 dB per decade. So that steep also depends on the number of poles present, right?
Uh, yes. So that means that as the number of poles increase, so the instability, we are going towards instability, right?
Yes, yes.
Okay. Oh, right. Thank
So
you.
the range at which your system is stable, that reduces. The frequencies at which your system is stable, that reduces with
Okay.
increasing
Okay.
number of poles.
Right. Thank you.
Because you can see, right? Like for two poles only, we are put at a spot. So it's not like
Yes.
two pole system is stable for all the frequencies. There are certain
Yes.
frequencies at which definitely your two pole system is unstable. Now imagine the more you introduce new poles, the frequencies at which like the range of frequencies at which your system becomes unstable, that certainty increases even more.
Yes.
So yeah, but we know that in a single pole system, no matter which frequency you take an infinite frequency, till that also your system is stable, because you will always find a phase margin, like maximum phase margin of 90 degrees. So it is always
Yes.
stable, but that is not the case for second order. And the more you increase the order, definitely your stability reduces. So that also
Right.
can be related to the bandwidth. Basically, bandwidth, by here, the bandwidth I mean is the operating frequency range. It's not about, now I'm not concerned about the reliable output, rather whether the system can survive or not. So I'm talking
Mm.
about that bandwidth. So the more the
Uh,
poles, that bandwidth, that until this frequency only, it will be stable. So higher the
right.
number of poles, that frequency range will start reducing, for which the system works as a stable system. Because this,
Okay.
see, here you are calculating phase margin at 0 dB point, right? So the
Yes.
possibility is कि 0 dB pe the frequency was, let's say, 1 megahertz. Beyond 1 megahertz, definitely your system is unstable. But before that, there are chances that it is stable, right?
Yes.
Because it ultimately depends on the values that you calculate. So ऐसा नहीं है कि if there is a 8-pole system, for example, it will never be stable. That is not true. It could be stable at certain frequencies only. And those frequencies will be very small and very less compared to
Okay.
when there is a single pole system, which is always stable. So it is stable for all the frequencies. So that is the idea,
Right. All right.
right?
Thank you.
Yeah. Okay. So now, when we have a two-pole system, so um, okay, it's going a little lengthy, but I guess it is important, so maybe we'll take it up. When we have a two-pole system is defined with a transfer function as A upon, or maybe I will write. So this is how the two-pole system is defined. Now, if we see um, the value of or the DC gain of the system. DC gain means the frequency is zero. Then the gain of the system is ADC. And this is how simply you represent your two-pole system. And if I have to open this up, so it will become omega 1, omega 2 upon s square plus 2s s square plus s into omega 1 plus omega 2 plus omega 1 into omega 2. So this is how your transfer function will look like. So the common way of representing a two-pole system, common two-pole system representation. So common two-pole representation is like h of s is given as omega n square upon s square plus 2 alpha omega n s plus omega n square. Okay, so this is how a two-pole system is generally represented. So this is the uh, most common way of representing a two-pole system. Now here omega n is a constant where omega n is given by, so all these things that we are discussing right now, these come from control systems. If you go through like control system textbooks or control system lectures, so these are the part of control systems where this is how, but all the systems which are present, they are generally analyzed for stability in the similar manner. Okay, so omega n is given by this. Now 2 alpha omega 1 omega 2 is omega 1 plus omega 2 from above. So what we are trying to do is we are relating these two, okay? And from there we are finding the values. So 2 alpha becomes omega 1 plus omega 2 by uh, 2 alpha omega 1. So this is ADC omega 1 omega 2. So this is 2 alpha, where this 2 alpha is known as damping factor. So this damping is this damping, the damping that we discussed here, right, in the beginning. So this is the damping that we are talking about. So that factor basically tells you about the damping, what type of damping will be introduced in the system, and so how your final this would look like. So now let's say case one. In this case, I say so this is a two pole system. I say my both the poles are at same position, omega p. Okay, both the poles are at same position, which brings me to the point that okay, so omega n becomes root under ADC into omega p, and 2 alpha will become 2 omega by root under ADC into omega p. So this is 2 by root ABC is 2 alpha. So alpha becomes 1 by root under ADC. So this is definitely less than 1, correct? So alpha is less than 1. For ADC, definitely greater than 1. Now when alpha is 0, if we see from this particular expression, if alpha becomes 0, the transfer function will become omega n square by s square plus omega n square. Correct? So this brings us to having two poles is equal to plus minus omega n, right? And we know that this is a constant. So this is real. So when we have two real poles, how does the system look like? Oh, sorry. Uh, this is imaginary because omega n is real, but see, s square is minus omega n square. Now s will be plus minus omega n j. So omega n is real, but j omega n is imaginary. So which brings us to having two poles, one here, another here on the y-axis, and we know that it is a marginally stable system, correct? We discussed this. So we know that this is a marginally stable system. So this is for alpha equal to 0. Now if alpha is 0, then it is marginally stable system. Now the second case is when omega 2 is much much greater than omega 1, that is, one pole is far away from another. So for example, let's say omega 2 is 4 times of omega 1 to start with. So 2 alpha will become omega 1 plus omega 2 by root under ADC omega 1 omega 2. That is 5 times of omega 1 by root under ADC into 4 omega 1 square. So that is 5 by 2 root under ADC. So alpha is 5 by 4 root under ADC. Now if I write it like omega 1 plus omega 2 of whole square root under by root under ADC omega 1 omega 2 omega 1 square omega 2 square plus 2 omega 1 omega 2 by ADC omega 1 omega 2 whole divided by, so this will become 2 times, this becomes omega 1 by ADC into omega 2 plus omega 2 by ADC omega 1 plus 2 by ADC. Now here we know that omega 1 omega 2 are related because omega 2 is 4 times of omega 1. So this will उसको substitute करके we will get simply 1 by 4 ADC plus 4 by ADC plus 4 by ADC. That is now 1 by 4 ADC. We know that ADC is much much greater than 1 because this is the gain. So we can neglect this. So we are left with 4 by ADC plus 2 by ADC. So overall, by using all of these and simplifying the expressions, at the end, what we come across is alpha becomes almost equal to 1. By using all these, we say that the alpha becomes almost equal to 1. And when that is the case, your transfer function becomes omega n square by s square plus 2 omega n s plus omega n square. So this is omega n square by s plus omega n whole square. So here we are left with poles of s equal to minus omega n. So we have two poles which are real and in the negative s plane. So when we have two real poles in the negative s plane, then we know how our output becomes an overdamped system, right? This we discussed earlier also. So this is your output and this is your input. So when you have alpha equal to, so the idea of basic this analysis is when your damping factor becomes zero, you get a marginally stable system. When you have a damping factor of 1, your system becomes overdamped. So that's how your damping factor works. So more the damping, it will become overdamped. If there is zero damping, then it becomes marginally damped. Now, the third case is when alpha is less than 1. Oh, sorry, when alpha is greater than 1. So when alpha is um, so this system will again be a stable system. We will get two poles with alpha being greater than 1, and it will be somewhat like the this kind of system, which is the damped system. Yeah, so this is your input and this is your output. So this is how the system will look like. So yeah, so that's how the alpha or the damping factor basically defines your behavior of the system. So most of the times we comment on the system uh, based on this alpha factor. So we define the second order system in this format. That is, whatever the transfer functions are, we uh, bring them to this particular format, and from here we find the values of alpha, which is the damping factor, and based on the damping factor values, we comment whether the system is stable, marginally stable, overdamped, or unstable. Okay. Now, yes, see here, if I have a negative instead of positive, so you know that if there is a negative over here, that means at least one factor would be S plus, sorry, S minus something, correct? So when you find the pole of that system, it will give you a positive pole. So that is the right hand side pole. So which will definitely make your system unstable. So that's how from just by looking at the transfer functions, we comment on uh, the stability. So the whole idea of this analysis was that. Now, if I talk about the Bode plots, so we know the Bode plots, right? How we use the Bode plots. So the Bode plots are used for. So first of all, we have two types of Bode plot. That is gain plot, or I should say magnitude and phase plot. Magnitude plot and phase plot. Now, if we talk about the uses of Bode plot, so it defines first of all the stability of the system. So we can determine the stability of the system by looking at the crossover frequency and finding the phase of system. Secondly, we can also define the functionality of the system. So it's like So uh, just a minute, I'll be back in a moment. Okay. So yeah, we were talking about how a body plot can be used, first of all, to understand the stability or to identify the stability of the system. And secondly, is to find the functionality of the system. Now, how do we talk about the functionality of the system? That is done. Am I audible? Okay. Yeah. So that is done by, let's say you have a body plot. Okay. So if you have a body plot like this, which is a magnitude plot, and if I say my body plot looks like this. So by looking at this, if I have to comment on the functionality of my system, so this is a low pass filter. Okay, so this is a low pass filter. In the similar fashion, if I have my body plot like this, so this shows me a high pass filter characteristics. Now, if I have a behavior like this, then this is a band stop filter. as it restricts the passage of certain few frequencies. So that's why we call it a band stop filter. If this type of behavior is observed, then it is a band pass filter. So you can see that all these transfer functions or Bode plots talk about the functionality of the circuit. Now, if I have, let's say my Bode plot, magnitude plot looks like this, then what can I comment on the behavior? If my Bode plot is a straight line, then what can I comment about it?
All pass filter.
Yes, it is a all-pass filter. So the question arises, why do you need an all-pass filter? If everything is passing through it, is there a point of having an all-pass filter? Okay, so that comes from the phase analysis of the circuit. Okay, so it appears that when you have a all-pass filter, the phase of the all-pass filters look somewhat like this. And the all-pass filter, what it does is it basically introduces a phase shift between your input and output. So it's like if you have an input sine wave like this, so this is input. So the output will look like this. So it introduces, this is an output and it introduces a phase shift on 90 degrees. So it can introduce any phase shift, but here we are talking about a 90-degree phase shift. So this basically is this particular all-pass filter is used to introduce phase shift into the system. A phase shift, if we talk about phase shift in times perspective, it is basically the delay. So it introduces a certain delay in the system. Okay, so if you have to introduce some delay in the system or you want to introduce some phase shift, so phase shift and delay are analogous to each other. So that is done by the all-pass filter. So from here, we can clearly observe that from Bode plot, we can comment on the stability by looking at its crossover frequency and phase analysis. We can also comment on the functionality of the circuit, like what is the function of that circuit. Yes, any doubts?
Yes, so in this the all pass filter,
Yeah.
so the delay that is introduced is frequency dependent.
Yes, it is frequency dependent.
Okay, so it's not a constant phase delay. So a
Yes,
particular
it
depending on a
changes.
particular frequency, it will change.
Yes, yes.
Uh, is it
Depending on the
useful in that
particular
case?
frequency. I mean, it's like at what frequency you are operating to introduce what delay. So if you want to have a like if you want a delay of 45 degrees, then you will design your all-pass filter using the components as such that it would provide you with 45 degrees of delay. So this phase profile that you observe, so here in all pass filter, what happens is here also you have a pole and zero. So it's a pole zero system. But what happens is the pole and zero values coincide with each other. So that is the reason that you don't see any uh, change in the profile, like frequency profile. But those poles and zero values can be changed, right? It depends on uh, the components that you use, like the resistances and capacitances that you use, correct? Based on that,
Yes.
your this pole and zero location will be there. And based on the poles and zero locations, your phase shift will be defined. So it at
Okay,
the end
so
comes down to the components. So defining the components can change the value of the phase shift.
So that means, yeah, I mean, tuning in the components is the main thing
Yes,
in this case.
yes, yes, yes.
Um,
Even it is true for all of them. So let's say if I design a low pass filter, where do I want my cutoff to be? So I can design a low pass filter for 10 kilohertz. I can design a low pass filter for 1 megahertz. So the transfer
right.
function will look similar. What is changing is the component values. Because depending on the component values, your cutoff frequency will change and hence your profile. So it again boils down to the component values.
Right. Okay.
But
Thank you.
yeah, the component that you use will define your frequency behaviors. Okay. So yeah, with these, maybe let's solve at least one problem today. And if time does not permit, we can take up them in the next session. Like, yeah, to start with, this is question number one. So in this question, so you have a two-stage cascade amplifier as shown below with the GM1 as 323 microsiemens, GM2 as microsiemens, R1 71.2K, 9.7K, 682 ampere, 3640 ampere. This is 20 watt. The design is to be compensated for a phase margin of 75 degrees. What should be the ratio of two poles of the circuit? Give your answer as greater than 1. Okay, so here the idea is we want our system to provide us with a phase margin of 75 degrees. For that, we need to define the ratio of poles. So predominantly, the two poles that will appear in our systems are R1 C1 and 1 upon R2 C2. So these are the two poles that will appear in the whole in this circuit. So if R1 C1 becomes equal to R2 C2, that means both the poles become equal, then we know it is a marginally stable system. If both the poles become equal, then we have a marginally stable system. But if we have like R2 C2 greater than R1 C1, that is the output pole, the output side pole, which is greater than input side pole, so it becomes a stable system as there is separation between the two poles. So R2 C2 by R1 C1 should be greater than 1 for having a stable system. Now, since this is a cascade system and the gain of a cascade system can also be denoted as GM1, GM2 into R1, R2. That is the output resistance is coming from here. So the ratio of poles is given by A naught square minus 1 by 1 plus A naught cos phi, where phi is phase margin. So this particular expression minus 1 plus A naught cos phi. Okay. So this particular expression to find the ratio of poles has been discussed in the lecture. So this is the formula I have put from the lecture. You can go through it in detail. So in this particular formula, when we place the values of A naught, and from there we can find the value of this X, with phase margin is given as 75, right? So phi is 75. So phi is given, A naught is given. From there, we can find the ratio of poles, that is X, and it turns out to be 810.98. So this is the ratio between two poles. Okay, so for this particular expression, you can go through the lectures and you can find out. Okay, coming to the second problem. So in this problem, the design is to be compensated for a phase margin of 75 degrees by adding an extra capacitor in shunt to C12. So shunt means parallel to C12. What should be the value of CC? So we want to design to compensate the phase margin of 75 degrees. So compensation has to be done by adding a capacitor in parallel to the wave. In parallel to this particular capacitor, that is C12. So another capacitor CC will be placed here in parallel to C12 in order to compensate this. So if we see that the CC and C12 are in parallel, and as this is an capacitor between two nodes, so this is a Miller capacitor, the combination on itself, and this capacitor will come, one part will come in parallel to C1 and another part will come in parallel to C2. So these values will further change the values of capacitor C1 and C2, and by that we can further separate the two poles. So if we talk about the transfer function that will appear because of this normal figure is R2 1 plus S C1 R1 plus C12 R on 1 plus S R1 C1 2 plus R2 C2 R1 C1 plus R2 C1 2 plus J2 R1 R2 C1 2 plus S square C1 C2 plus C1 C1 2 plus C2 C1 2 R1 R2. So from this analysis, we basically what we understand is we would get two poles and one zeros that we already know because these poles, so here and here, so output of both the stages will give us one pole, and this particular capacitor, that is C12, which is connected between the two nodes, two prominent nodes, will give us a zero. So we already know that there will be two poles and one zero. So if we write like the two poles, so it is 1 plus S tau 1, 1 plus S tau 2. So that is 1 plus S tau 1 plus S square tau 1 tau 2. So this tau 1 can be given as 1 of R1 C1 2 plus R2 C2 R1 C1 plus R2 C1 2 dash plus C1 2 R1 R2 C1 C2, where C12 dash is the parallel combination of Cc and capacitor C12. Okay, and tau 2, that is 1 upon omega p2, can be given by C1 C2 plus C1 C12 dash plus C2 C12 dash R1 R2 by R1 C12 plus R2 C2 plus R1 C1 plus R2 C12 dash plus B into R1 R2 C12. So the X, that is the ratio of the two poles, is tau 1 by tau 2, that is P2 by P1. This is given by C1 C2 plus C1 C12 dash plus C2 C12 dash R1 R2 by tau 1 square. And we know that the ratio of poles from the previous problem, we have used the formula A naught square minus 1 by 1 plus A naught cos phi minus 1 plus A naught cos phi. So here we have seen that x is also which is also a function of c square, sorry, C12 square, 12 dash is 810.98 degrees from the previous problem where phi was 75 degrees, A naught is GM1, GM2, R1, R2. And since it is a quadratic equation, so C12 dash should be the solution of the quadratic equation, correct? So that is minus b plus minus root under b square minus 4ac by 2a. And by solving these values, what we find out is a is 6, 2, 5, 4, 8, 7, 8, 8, 4, 3, 4, 3, 5, 5, 3. Okay, B is minus 2.28809, and the value of C is minus 1.3834 into 10 to the power minus 12. Now from here, by putting all of these into this, we can find the value of C12 dash, which is also equal to CC plus C12. So the value of CC becomes C12 dash minus C12, which was 20 femtofarad given in the question. So from there, when we substitute and solve, the value for CC, that is the compensation capacitor, comes out to be 4166.398 femtofarad. So this is the value that we obtained for the compensation capacitor. Okay. Now, in the similar manner, if there is a resistor that has to be placed in series with the compensation capacitor to cancel out the main right hand side pole, right hand side zero caused by the short circuit current, what should be the value of this resistor? Give your answer in ohms. Okay, so here the idea is to place a compensation capacitor and resistor along with it. So this is RC, this is CC. So we have to find the value of, here we get the pole 1, at this point we get pole 2, and the value of RC such that the right hand side 0 is cancelled out. So CC is 4166.398 femtofarad. From last question, this was 20 femtofarad. RC is something that we need to find out. The right hand position 0 is given by GM2 by CC upon 1 minus GM2 RC. So we want the right hand side 0 to be infinite. It should be placed at infinite. That 0 to be very far away. So from there we can say that 1 minus GM2 RC to be 0, which brings us to RC as 1 by GM2. And since GM2 is 1028 microsiemens, so RC comes out to be 972.762 ohm. So again, this formula can be observed in the lectures. So you can find it from there. And this is how we can solve this problem. So yeah. So these are few problems based on how we deal with phase margin and how compensation capacitor and series with resistor are used to improve the stability of the system, introduce stability, and handling the zeros as we have done in the last problem. In this problem, the compensation capacitor basically introduces a zero. So this has been analyzed. And in the first problem, we were finding the ratio of the ratio of the poles by using the phase margin. So you can go through these problems once again. And these formulas have been discussed in the lectures. So you can go through the lectures as well. So yeah, that's all for today. If you have any doubts, feel free to ask, or else we'll meet in the next session coming week with new set of problems.
Thank you, ma'am.
So I know there was a lot that we discussed today, and so please try to go through the lecture notes as well as the uh, like the video ones. In case you feel there are some problems or something you feel like discussing, we can discuss them in the coming session next week. So yeah, if there are no other doubts, we can break over here and meet next week. That's all for today. Thank you. Thank you for joining.
Thank you.
Thank you.